Right. Hey guys, welcome back. So this is going to be part 2 to our Unit 0 for AP Chemistry. You should have already watched the part 1 video, and this is going to be the second part of what we've already learned in 10th grade chemistry, whether it was on-ramps or advanced chemistry, right? And so remember in part 1, we had 2 new topics. We talked about mass spectrometry, and we talked about orbital diagrams with electron configuration. And this part, nothing's going to be new, but it does have some tricky concepts that might have been difficult, so we'll just need some practice. All right, so in this part, we're going to talk about things like reactions, bonding. We're going to draw some Lewis dot structures, name some compounds, and then we'll do a little bit of math. We'll talk about scientific notation and stoichiometry at the end. All right? So starting off simple, we have physical versus chemical reactions. Remember, anything that's physical change, physical reaction, it's something that is reversible, that the objects can be separated out. You're not making something new. You're just changing what it looks like, right? So some examples are ripping paper, phase changes, or mixing things together. Phase changes can be tricky because it looks like you're making something new, but if you go from ice to liquid water, you still have water. You still have H2O. It's just the molecules are arranged differently. That makes it look different, right? But phase changes, so melting, freezing, condensing, evaporating, those are all physical changes because what you have stays the same. The water goes from ice to liquid water to steam or water vapor. But wherever it's at in that process is still water, still H2O. With chemical changes, these are not easily reversible. You cannot separate them out, and you are making something new. And you may remember, when you're making something new, a new product, this can be, or we can see this with color changes. If there's a gas forming, if there's bubbles, a precipitate, that's a word that we should know. We talked about this with, I don't remember if you remember, but we mixed sodium iodide with some lead nitrate. And those are two clear, colorless liquids. And when they were mixed together, it made some yellow. That yellow is our precipitate. So precipitate is when you mix two liquids together and it makes a solid. Okay? And then also if it makes an odor, that means something new was made. Okay? As chemical reactions also typically have a change in energy, whether that's heat, light, or sound energy. Some examples are rusting, burning wood, cooking, digesting your food, fireworks, and batteries. Those are all chemical reactions. When we're talking about chemical bonds, right, when we're talking about atoms bonding together, we have 4 different ones that we're going to talk about. The main 3 are covalent, ionic, and metallic. So covalent, remember that's 2 nonmetals. Remember when we say metal, nonmetal, if we have the periodic table, I'm just going to draw a square up here for the periodic table. We have that staircase on our periodic table. The top or the right side of it, those are our nonmetals. The left side is our metals, right? So covalent, we're only on that right side. We're only talking about nonmetals. And they're sharing electrons. So in this image here above, you can see that the 2 electrons, it overlaps. It's like a Venn diagram because they're sharing. Okay. For ionic compounds, you have 1 metal, 1 nonmetal. So it's 1 atom on opposite sides of that staircase, and they're transferring electrons. So in the image here, you can see that the atoms are still separated. They're not overlapping. The electron was either given away or taken. And remember, our metal, like Na, sodium, that's going to give away an electron. And if you lose an electron, it becomes positively charged. And then our nonmetal, our chlorine, is going to gain the electron. If you gain an electron, it becomes negatively charged. Remember, positive charge is a cation. Negative charge is an anion. Okay. And the third type, metallic, is what it sounds like. It's between 2 metals. So we're only on the left side of the periodic table. And this is what we call a sea of electrons, right? So in the image, you can see those blue dots. Those are our electrons, right? So all these electrons, they aren't attached to a single atom. They're kind of floating in that white space. They go in between, they're shared between all the atoms in the middle. So that's why we call it a sea of electrons. That's why metals are typically good conductors. Right? And then the fourth one is covalent network solids. This is very similar to covalent, right? You have nonmetals, you're still sharing electrons, But these form larger structural orders, right? So if you look at the image, you can see like graphite, you have these hexagon shapes that are attached together and they form layers. So this one here is going to be one layer. The four on top is going to be the second layer. They kind of stack on top of each other. Diamond on the right side, you can see it forms an even more complex structure. So these are still, they're made of carbon, but the way the atoms arrange themselves makes it stronger and have different properties. But it's still non-metal, so it's still covalent. Okay. Some examples of covalent network solids that you should know on the bottom here: graphite and diamond, those are made with carbon. And then quartz and glass are made with silicon dioxide, SiO2. Okay, so those are some common examples that you should probably remember. Okay, so going on to naming, right? Remember, we can go from the formula to the name, or from the name to the formula. If you're in advanced, you saw the same table. On-ramps, I don't know exactly how you're taught naming and writing formulas, but essentially it's going to be the same rules, right? So on this first group here, from the formula to name, we're going to follow the left side if it's ionic, the right side if it's covalent. Let me do covalent another color. Okay, so for ionic, your first step is you're going to write the name of the metal as it is on the periodic table. The second step is write the nonmetal ion with the IDE ending, right? So the IDE ending is if you take, for example, chlorine, you're changing the ending to ide. So instead of chlorine, it's chloride. Okay. For covalence, you're going to do something similar. You're going to take the first nonmetal without changing its name, write it as it is on the periodic table. The second step is you're going to write the second nonmetal with the IDE ending. Same thing we did for the ionic. The way this is going to be different is we're going to add prefixes. And remember, your prefixes are over here on the right. Okay, so for example, if we have CO2, right, we have one carbon. So I'm going to start with carbon. And I have two oxygens. The oxygen becomes oxide with the IDE ending. And then we're going to add our prefixes. For carbon, we only have one, right? So that would be mono. But a special thing with mono, make sure you note this down or remember this. You don't put mono on the first element. So if the first element is carbon, we only have one, it's going to stay as carbon. We're not going to write monocarbon. Okay. For the second one, for oxygen, we have two. So 2 is di. I'm going to put a di in front of oxide. So we have carbon dioxide. Okay. And we'll do some more examples here in a minute. But for going the other way around, from the name to the formula, right? Again, if we're ionic, we're going to do the left side. Covalent is the right side. So going from the name to the formula, right, that we're writing symbols. So the first step is you're going to write the symbol and the charge of the metal. So like, for example, sodium would be Na+1. Second step is write the symbol and charge of the nonmetal. So chlorine or chloride will be Cl-1. And then do the crisscross method. I'm going to zoom in a little bit here. Remember, the crisscross method or the butterfly method is you're going to take the numbers on top, the charges, and put it on the bottom of the other ion. So our Na is going to take the -1 charge from the chlorine. It's going to go on the bottom, and we're just going to write the number. We're not going to write the charge, so just 1. Same thing with chlorine. It's going to take the +1 from the sodium, put it on the bottom, but remember without the sign, just the number, so 1. So sodium chloride is NaCl. You have 1 of each. It might make some, let me do one, or there's going to be examples with other numbers. So I am going to leave that at that, but I'll do more examples here in a minute to make more sense. Okay. For covalent, you're going to write the symbol of the first nonmetal, and then the subscript, the number on the bottom, is going to match the prefix on the right. So for example, if you have penta, you're going to put a 5 underneath it as subscript. Then you're going to write the symbol of the second nonmetal, and the subscript, again, is from that table. Okay. Remember, with writing formulas and names, we do have polyatomic ions. Polyatomic ions are groups of nonmetals that come together and they have an overall charge. So if you look at this table on the right, every group of nonmetals, they all have a charge, right? So if it's a plus, that's a +1. Minus is a -1. If it has a number up there, that's a charge. So -2 for sulfite, right? And when they're bonding, they are going to form ionic bonds with metals because it has a charge already. Okay, so these polyatomic ions on the right, these are the more common ones. You should memorize these before the AP test, right? These will come up. So things like ammonia, nitrate, nitrite, sulfate, hydroxide, phosphate. Those are some of the more common ones, carbonate. So those ones are the most common ones, but I would remember this whole table. Remember those ones I mentioned first because those are more likely to come up on your test or on your practices. But over time, make sure you remember this whole table. Okay. All right, so let's do some practice with this. So these ones we're going to convert from the name or, this is mixed. We're either doing a name or formula for all of these below. Okay, so remember formula, that's when we have the letters like NaCl. The name is when we actually have the name of the elements written out. Okay, so this first one, NaCl, right, following the steps. The first step is to determine if it's ionic or covalent. Sodium's on the left side of the periodic table, chlorine's on the right side, right? So if we have both sides of the periodic table, this is a metal. Oh, that's a weird name. Metal and a non-metal. So this is going to be ionic. All right, so the steps for ionic, for naming, is we're gonna write the name of the first metal, or the name of the metal. So Na is sodium. And then we're gonna write the name of the non-metal. So chlor, and instead of writing chlorine, we change the ending to IDE, chloride, so sodium chloride. Okay. For SRO, right, we have strontium. It's on the left side of the jagged line. Oxygen's on the right side. So if we have either side, one metal, one non-metal, this is again going to be ionic. So we're going to write the name of the metal, strontium. Let me write that a little better. Strontium. And then write the name of the non-metal with the IDE ending, oxide. Okay. For ALN, we have aluminum. That's going to be on the left side of the jagged line. N is nitrogen. That's on the right side. This is ionic once again. So the name of the metal is aluminum. The non-metal with the IDE ending, IDE ending is nitride. Not nitrogen, nitride. Okay. I'm going to leave this second row for you to do. Okay. You should get barium chloride, potassium oxide, and then copper oxide. Okay, so make sure you do these. Make sure your answer is correct. If you're having trouble with this, make sure to ask questions. Okay. If we're going the other way around, if we have names and we're trying to figure out the formula, you're going to do the same thing. Figure if it's ionic or covalent first, then follow the steps that I gave you in the previous slide. Okay, so first we have magnesium. Magnesium's on the left side. Nitride is nitrogen, that's on the right side. So this is ionic. We have opposite sides of the periodic table. Okay, so remember for ionic, we're going to write the symbol and charge of our metal. So Mg+2 for magnesium. Symbol and charge of our nonmetal, N-3 for nitrogen. And then we're going to do the crisscross method. So the -2 is going to go to the bottom of the nitrogen, +3 goes to the bottom of the magnesium. So we get Mg, remember without the sign, so just the 3, and then N2, the 2 came from the magnesium. Okay. Okay, so hopefully that helps you see that crisscross with the butterfly method a little easier because there are different numbers there. Okay, for barium bromide, barium's on the left side, bromine or bromide is going to be on the right side, so it's ionic. Okay. Barium has a +2 charge. Bromine has a -1 charge. So if we switch these around to the butterfly method, we get the Ba1 and then the Br2. Okay. And when you're going through these, for the ones, you don't have to write those in, but if you do write it in, it is not incorrect. It's correct either way. Okay. And remember, these charges, I'm getting these from when we labeled the periodic table. We labeled the groups or the columns with a specific charge. That is the number I'm using there. Okay, so barium is in the second group, has a +2 charge. Bromine is in group 17, has a -1 charge. All right, and then our last example that we're going to do together for this slide, 10 for bromide. Remember your Roman numerals, right? So we have 1, 2, 3, 4, 5 is I, 4 is IV, 5 is V. Make sure you remember those. Okay, so the reason these are important is because this will tell us the charge. So 10 is SN, and that's a middle. Bromide is BR, it's a non-middle. We know the charge of bromide, but 10, we don't know the charge of it. Okay, so 10 does fall in group 14, right? So we said that one's ±4, but 10 kind of falls under the transition middles where it can have different charges. It can be +4, it can be +3, it can have different charges. So this Roman numeral tells us what charge it is. If we have Roman numeral 4, it's a +4 charge. Okay, and then from here we do the same thing. We're going to do the butterfly method without the signs. So SN1, BR4 for 10 bromide, 10,4 bromide. Okay, and then again, I want you guys to do these last three. So potassium iodide is going to be Ki, sodium fluoride is NaF, and lithium chloride is LiCl. I left some easy ones for you. Okay, so work through those, make sure you get those same answers. If you're not sure, make sure you ask questions. All right, so moving on to Lewis dot structures. Remember, we use these Lewis dot structures to visualize what the compound looks like, to talk about its geometry. Okay, so again, if you were in advanced, you've seen this before. On ramps, you might have seen something different, but it's the same process. Okay, so this top table is going to be for covalent. The bottom table is for ionic, or the bottom square, the boxes. Okay, so steps for doing covalent. So let's do this together. We're going to do step by step for NH3. Okay, step 1 is we're going to add the total number of valence electrons for each element. All right, so the valence electron, remember, we get that from the group numbers. So nitrogen is 5, hydrogen is 1, but we have 3 of those, so 1 times 3. And we're going to add them up for different elements. 5 plus 1 times 3 is going to be 8. We have 8 total valence electrons. We're going to write the element so that the least electronegative is in the middle, and H is never in the center. Okay, so we have N and H. If H is never in the center, we're going to have nitrogen in the center, and then we're going to write the other elements around it. So we have 3 hydrogen, going to put 3 hydrogens around it. Make sure you never add more atoms than what you have, right? I only have 3 hydrogens, so I'm not going to put 1 on top also, because I don't have 4. I only have 3. Step 3 is that we're going to put a bond between each element. Remember, a bond is a line. It's going to be the line connecting the elements, and that line is equal to 2 electrons. So we just did 2, 4, 6 electrons. And in step 4, we're going to add the remaining electrons to the outer atom. Okay, so no atom should have more than 8. Right now we have 2 on each hydrogen. But down here at the bottom of the box, we have some exceptions. Hydrogen is one of those exceptions. Hydrogen only gets 2 electrons. It does not get more than 2. Okay, so these hydrogens already have 2 because that line is 2 electrons. So we're going to stop there for hydrogen. Step 5 is add any lone pair of electrons to the central atom. Remember, our lone pair looks like 2 dots. It's 2 electrons, 2 dots. So on the central atom on our nitrogen, we're going to put those 2, that's a weird dot. We're going to put the 2 dots. Okay, and in step 6, we're going to make sure everything follows the octet rule or follows the exception that it has. So hydrogens, we said need 2 electrons. They each have the line. That line is 2 electrons, so we're good. Nitrogen wants 8 electrons. So on nitrogen, we have 3 lines, so that's 2, 4, 6. And the 2 dots on top is 7, 8. So that has 8 electrons. That is good. So if everything's happy, everything has the amount of electrons it needs, we're done there. That is the Lewis dot structure for a covalent compound. For ionic compounds, right? So we'll do this for MgCl2. When you're doing ionic compounds, you need to know the charges. So here, Mg has a +2 charge. Cl has a -1 charge. There's 2 ways you can figure out the charges. What I just did is I know them based on the periodic table, right? Mg is in group 2, it has a +2 charge. Chlorine is in group 17, it has a -1 charge. You can also do a reverse butterfly method. So if you have Mg, you have 1 there. Cl has 2. You can move these numbers to the top of the opposite compound. Or sorry, not the opposite compound, opposite element. So the Mg gains the 2, and since it's a metal, it's positive. The Cl gains the 1, and since it's a non-metal, it's negative. Okay, so we have our elements, we have our charges. So step 1 is we're going to write the symbol of the metal, so Mg, and we're just going to leave it as is. We're not going to put anything around it. Step 2 is write the symbol of the non-metal, so Cl. We're going to put 8 dots around it, 8 valence electrons. Step 3 is place brackets around the elements. You don't have to put around the metal, but you do have to put around the non-metal. And in step 4 is add the charges outside the bracket. So we said Mg had a +2, sorry, and Cl had a -1 charge. Okay, this one we're not quite done because if you look at our compound, we had MgCl2. We have 2 chlorines, so I need to either put a second Cl in here with the 8 dots and the -1 charge, or what I can do is I can do the Mg +2. I can draw out the Cl, the -1, and I can put a 2 in front of that Cl because that shows that I have 2 of those chlorines. Okay, either one of those is acceptable. Okay, so hopefully that helped jog your memory for drawing some Lewis dot structures. We're going to do this third one together. I'm going to let you guys do those first 2, so practice doing those. You already have the answers. We're going to do this third one. So C2H5OH. These are all nonmetals, so it's a covalent compound. Step 1 is find the total number of valence electrons. Carbon is 4, and we have 2 carbons. Hydrogen is 1, and we have 6 hydrogens. We have 5 here, 1 on the end, so that's 6 total. And then oxygen, is 1 times, that has 6 valence electrons, so 1 times 6. Okay, so we have 8, 6, and 6. If we add those together, we get 6, 12, we have 20 valence electrons. Okay. The second step says to put the least electronegative in the center. So remember, hydrogen's never in the center. We have 2 carbons and we have oxygen. Carbon is the least electronegative here, but we have 2 of them. So when you have 2 carbons, they're both going to be kind of central atoms. They're going to go side by side. And we're going to put the other elements around it. Okay, so we have a hydrogen, or we have 5 hydrogens, so 1, 2, 3, 4, 5. And then we have an OH. That OH we're going to keep together on the same side. The next step is draw a line between each of the elements, right? So these 2 carbons go together. and we're going to draw a line between each of the elements. Okay, so why didn't I draw a line from this hydrogen to this carbon? Well, if you look at that carbon, it now has 2, 4, 6, 8, 10 electrons. That's not going to work with that octet rule, right? So that can't happen. Okay, and then we don't have any remaining electrons because we have 2, 4, 6, 8, 10, 12, 14, 6, or we do have remaining electrons. We have 16 electrons, right? We need 20, so we need 4 more electrons. Where those 4 electrons go? So which elements are not following the octet rule right now? The carbons have 2, 4, 6, 8. 2, 4, 6, 8. Those are good. Hydrogens each have 2 electrons on them. Remember, they're an exception. They only want 2. That's good. Oxygen has 2, 4. Remember, oxygen wants 8. So on this oxygen, we're going to put the lone pairs till we reach 8 electrons. So 2, 4 lone pairs. And now in total, we have those 20 electrons. Okay, so sometimes with bigger compounds, it can get a little confusing. Normally, these AP tests, these will be given to you, and you're just putting the lines and dots on there. You're not drawing the actual compound. But we need to make sure we know how to draw these. So anytime you have a compound like this, those carbons are the central atoms. They go side by side. Everything else goes around them. Okay. All right. So there is a list of draw the following Lewis dot structures. Let's do 4 and 5 together. Okay, so for question 4, we have N2, right? Nitrogen is a non-metal. We have 2 of them. That's covalent. So count the number of valence electrons. Nitrogen has 5 valence electrons. We have 2 nitrogens. 5 times 2 is 10. Okay, if you only have 2 atoms, there is no central atom. They just go side by side. Okay. We're going to connect them with our line, like we said, our bond. That's 2 electrons. We're going to put electrons on the outer atoms. So on this one, it's just either nitrogen until they get to the octet rule. They get 8. So we have 2, 4, 6, 8. 2, 4, 6, 8. And we're going to make sure everything follows the octet rule and we reach our 10 electrons. So each nitrogen has 8 electrons. But if we count our electrons, we have 2, 4, 6, 8, 10, 12, 14. We only want 10. So this isn't going to work out. So what's going to happen is we're going to have to make them share electrons. So we can take the electrons on the bottom and we can make them be shared as another line. And get rid of those. Okay, so now we have 2, 4, 6, 8, 10, 12. We're still over. So I'm going to take the ones on top and put them there. Put it as another line. Get rid of those. Now we have 2, 4, 6, 8, 10 electrons. That's what we want. Okay. So if sharing electrons doesn't make sense, make sure we ask about that. But this can only happen typically between the elements. So 2 of the same element or 2 different ones. But carbon, oxygen, nitrogen, and sulfur are some of the more common ones that this happens to. Okay. All right, so for question 5, NH4. With a +1 charge. Okay, so we're going to do the same thing. It's covalent. We have 1 nitrogen. We have 4 hydrogens. So hydrogen has 1 valence electron. We add those together, 5 plus 4 times 1. That's 9 electrons. But we have this +1 charge. +1 means we lost an electron. So it's going to be -1 there. So we only actually have 8 electrons. Okay. So we're going to put our nitrogen in the center because we have the only other thing we have is hydrogen. And that can't go in the center. Put our hydrogens around it. We have 4 hydrogens. Put a bond in between each one. make sure everything follows the octet rule and make sure we have 8 electrons. So each hydrogen has 2 electrons. That's what they want. They're good. Nitrogen has 2, 4, 6, 8. That's also good. And in total, we have 2, 4, 6, 8. That matches our number. So we are good. So that's that. When you're doing a Lewis dot structure for a charged compound, right, we had the +1 charge, gonna draw your Lewis dot structure, put brackets around it, and put the charge on the outside. Okay, so same thing, that's kind of how you would do for an ionic Lewis dot, but even though this is covalent, it's a polyatomic ion, it would form those ionic bonds. Okay, so make sure you try those other ones on this page. If you need help with it, ask questions, come into tutoring. You'll have some time in class to work through these. Or you'll have time in class to ask questions about these, but you should have these done before you come to class. Let me clarify that. Okay, and then the last thing with bonding, I believe, is VSEPR. Okay, so remember VSEPR is valence shell, electron pair, repulsion. So this means that we're looking at the valence electrons, only those outermost electrons. We are looking at pairs of electrons. And we're looking at how they're repelling each other, how they're pushing apart. Okay, so VSEPR helps us determine the electronic and molecular shapes of covalent compounds. Okay, we're only doing covalent here, not ionic. And this is going to be based on the central atom, what's around the central atom. Okay, so we have some definitions here. We have bonding groups. Bonding groups are the number of atoms attached to a central atom. So if we had that NH3, right, we have the 3 hydrogens and the lone pair. The bonding groups are those attached atoms. We have 3 bonding groups there. Lone pairs are the pair of dots, so 2 dots. So we have 1 lone pair there. In an electron domain, we're adding those together. So for NH3, that'd be 3 plus the 1. So we have 4 total there. Okay. And then we can figure out the electron geometry and molecular geometry. The electron geometry, we're looking at everything there. Molecular geometry, we're pretending that like that lone pair of electrons, it's invisible. We can't see it. Okay. So either way, you're still going to use this chart. You're going to look for the 3 plus 1. Right, so we have 4 electron domains. So electron groups, we have 4 of those. We have 3 bonding groups. We have 1 lone pair of electrons. So our electron geometry is tetrahedral. So if we're counting that lone pair of electrons, we have 4 regions of electron density. So it's going to be tetrahedral. For the molecular geometry, if we act like that lone pair of electrons is invisible, then we only have 3 things, but that lone pair is still acting on them. It's still kind of pushing them down. You can kind of see that in this image here on the right. Right, so when it's pushing them down, that makes it trigonal pyramidal. Okay, so remember with VSEPR, we talked about it briefly in advanced. You did more with this in on-ramps, but remember you need to make sure you memorize these geometries. You need to make sure you know the electron geometry, molecular geometry, and the bond angles for various examples. Okay, so some examples are here. Let's do number 5. Okay, so number 5, we've drawn this before. We have those 2 carbons with the 5 hydrogens and the O, the H. Okay, that was our Lewis dot structure. Okay, so for 5 and 6, we're going to do both these actually. For 5, we're looking at the carbon atoms. So for this carbon atom here, we have 4 bonding groups. It's bound to 4 atoms. We have 0 lone pairs. So we only have 4 electron domains. If you have 4 electron domains, 4 electron groups, you have 4 bonding groups and 0 lone pairs, that's going to be tetrahedral. Okay. For the second carbon, it's the same thing. You have 4 bonding groups attached to 2 hydrogens, a carbon, and an oxygen. You don't have any lone pairs, so in total you have 4. It's going to be tetrahedral. Okay. For the oxygen, it's a little bit different. You have 2 atoms it's attached to, the carbon and the hydrogen. You have 2 lone pairs of electrons. So it's still going to be 4, but you make 4 in a different way, right? So if we look at our table, we have 4 by having 2 bonding groups and 2 lone pairs of electrons. So our electron geometry is still tetrahedral, but our molecular geometry here is bent. And what bent means, shown here on the right, is it's kind of like a triangle with an open bottom, right? The angles, it's not going to be a straight line, it's a bent line. Okay. So with VSEPR, you can have a bigger compound like this and specify which element we are looking at, which atom. All right, so that is it for bonding. We're going to talk about a little bit about the math side of things. So with accuracy and precision looks at how, there are ways we can talk about data sets. Okay, so accuracy is when you are closer to your target. If our target is 6 meters long, the set that is closest to 6.000 is going to be set Y. Right, that's going to be our most accurate because it is closest to our target of 6.000. Precision means that your numbers that you got are all really close to each other. Okay, so if we look at set X has 0.864, 0.878, 0.871. They're not too far off, but these two are kind of far off. Right, set Y is 0.002, 0.004, 0.003. Those are all really close to each other, right? The furthest off is 0.002. Set Z, you have 0.873, 878, and 870. Not too far off again, but still those are it's a bigger gap. That's 0.008 off. So our most precise is also going to be set Y. But the reason is not because we're closer to 6.000, our target. It's because we have, or the numbers are closer together. Okay. And then for percent error, remember that our percent error, or here, let me talk about the percent error here in a minute. If you want to calculate that there, you can, but we'll have some examples here in a minute. Okay, so for accuracy and precision, accuracy is how close it is to the actual number that you're aiming for. Precision is how close your numbers are to one each other. Our percent error equation is right here. Okay, so it's theoretical minus experimental divided by theoretical, and then take the absolute value of that times 100. These bars here, that's the absolute value symbol. That means if you get a negative number, you're going to change it to positive. So if we do this math in the middle and we get negative 34, we're going to change that to a positive 34. Okay. Theoretical is what you get for stoichiometry. That's what I'm telling you you should have, right? That's what we get from the math. Experimental is what you get from your data, from your experiment. Okay. The closer you are to 0 here, right? Percent error, 0% error means that you're right on target. You're exactly where you need to be. Okay. When you're taking your experimental value, you'll normally take the mean of it. So if we go back to our table above, you'll normally take the mean of these. So for set Z, the mean is if you add your numbers together, so 5.873 plus 5.878 plus 5.870, and divide by the number of data points you have. So here we have 1, 2, 3, so divided by 3. And you would get 5.87, I can't do that in my head. 878, 874. Okay. So the mean is the average. You would put this number as your experimental value. Okay. Make sure when you're doing this in your calculator, you put these numbers on top first, click enter, then do the divide by 3. If you don't do that, if you just put in your calculator 5.873 plus 5.878 plus 5.870 divided by 3, based on PEMDAS, it's going to do this last bit first, then add your other two numbers, and that's not going to get you what you want. So either put parentheses around your addition parts, or do the addition first, click enter, then divide by 3. Okay. All right, so some examples. You have these on your paper. For this first one, we have a student determined that the molarity of HCl was 0.564 molar, that M is molar, by doing a titration. The actual molarity given by the teacher was 0.500 molar. What is the percent error? Okay, so here we have two numbers. We have a number that the student got by doing a titration, by doing the experiment. Then we have a number that came from the teacher. Okay, the number that came from the teacher, that's going to be a theoretical. That's what we should have gotten. So I'm going to put a T by that number. The number you got by doing a titration, that's what you got in the lab. That's an experimental number. So we're going to follow this equation. We have the absolute value of our theoretical, 0.500, minus the experimental, 0.564, divided by the theoretical, 0.500, absolute value of that, times 100. Okay. So where I'm going to put this in my calculator, I'm going to do 0.500 minus 0.564, enter, divided by the 0.500 on the bottom, and then do the absolute value of it. To do the absolute value, the easiest way is just take away the negative sign. So I got I got negative 0.128. So if I take the absolute value, just take away the negative, it's 0.128 times that 100 on the end, we get 12.8%. Okay. I want you to do the second one. You should get 13.14% here. Okay. And make sure anytime you're doing math, you show your work. So show yourself plugging into that equation there. Write that down on your paper. Okay. The second last thing we're going to talk about, scientific notation. This is a way to simplify these extremely large or extremely small numbers, right? Because if we talk about, say, Avogadro's number, that's 6022, and then 1, 2, 3, 4, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That is Avogadro's number, right? That's a very big number. We're not going to write that out every time. So instead, we do scientific notation. That's much simpler. It's easier to read. That's the point of it. Okay. So the steps to change a number into scientific notation are right in there. So we're going to move the decimal point until there's only one non-zero number to the left of it. So for the example here, we have 4,500,000. If there's no decimal point shown, then the decimal point goes at the very end. We're going to move it so there's only one number to the left of it, one non-zero number. So our first non-zero number here is going to be the 4. So we're going to move it 1, 2, 3, 4, 5, 6 times until we're before the 4. So we get the 4.5, right? We're going to get rid of those zeros to make it easier to read. And then those zeros get added on to the space here. So after 4.5, we're going to do times 10, and the number of spaces we jumped, that goes as the exponent. So we jumped over 6 spaces, we're going to put a 6 on top of that 10. So 4.5 times 10 to the negative 6 is our 4,500,000. Okay, it's the same thing if you have a number like this down here that's smaller than 1. We're going to move the decimal, so there's only one non-zero number to the left, which is the 4 there. So we get the 4.53, and we moved it 3 times, so we're going to put a 3 exponent. Since we moved to the right, this number is less than 1, we put a negative exponent. Okay, so it's going to be a negative 3 power. All right. If you are doing this the other way around, if you're going from a scientific notation to a number, let's do an example down here. Let's do this 4.2 times 10 to the 3. Right? We said if it's a positive exponent, we're making this number bigger than 1. So to make it bigger than 1, are we going to go to the left or to the right? We're going to go to the right. Right? So we have the 4.2. We're going to go over 3 times. 1, 2, 3. That's where our new decimal is. In these empty loops, we're going to put a 0. So we get 4,200. Okay. So let's do a couple of these. For this first one up here, 24,500. Changing this to scientific notation. Remember, if there's no decimal point shown, it's at the very end. We're going to move it so there's one non-zero number. Oh, sorry, I messed myself up there because of the comma. 1, 2, 3, 4. Okay, so we're going to write our numbers without the 0, 2.45. And then the times 10, we moved it 4 times, so it's a power of 4. If you have, so I'm saying to remove the zeros to make it simpler to read. If the zeros are either after your last non-zero or before your first non-zero, you remove them. If they're in the center though, like if you had a 0 here, instead of the 4, you would leave that 0 in your answer. You'd have 2.05 times 10 to the 4. Okay, I hope that makes sense. All right, 356. Remember, no decimal, put at the end. We go 1, 2. So we have one number left, one non-zero number. So we go to 3.56. We put the times 10. We move the decimal 2 times. Okay. Let's go down here to this number here. We're moving to the right this time, but we go 1, 2, 3, 4. So there's one non-zero to the left. So we get the 9.85. We moved it 4 times, so times 10 to the 4. And because this number is less than 1, we're going to put a negative there, negative 4. Okay. I'm going to leave these two for you all to do. Okay, so make sure to work through it. You should get 1.22 times 10 to the 4. And then either 5, or you can do 5.0, it doesn't matter. But 5 times 10 to the negative 17. All right, let's do a couple of these down here where we're changing out of scientific notation. So 2.159 times 10 to the negative 4. It's a negative number. We're going to make it smaller than 1, so we move to the left. So 1, 2, 3, 4. That's our new decimal point. Going to put some zeros in the empty loops. Okay, if there is a loop here that has a number, we don't put a 0 there. So our new number is 0.0002159, and that's it. Right? When we change it, we get rid of that times 10 part. When you're writing these numbers out, if you want to have 0 in front of the decimal, you can. It's the same thing. Just make sure that doesn't mess up your counting. Right? And then 3 times 10 to the negative 6. This one shows a decimal. Move it over 6 times. 1, 2, 3, 4, 5, 6. So our new decimal. Put our zeros in the empty spots. So we get 0.000005 zeros there. 3. Okay. And then try to do these ones on the bottom again. You should get 80 million for that answer. For this one in center, you should get 52300, so 52,300. And then 0.00004313. So 6 zeros, 4313. Okay, make sure you work through those. Make sure you get the same answers that I got there. All right, so moving on to the dimensional analysis, stoichiometry part. Remember, dimensional analysis we use to convert between our units because we have a lot of units in chemistry. Okay, so this is when we did either the railroad method that's shown here on the top right, or just the multiplying with the fractions. And advanced, we had a foldable that we used. Again, I don't know how on-ramps was taught, but if you have that foldable, as we're getting comfortable with this, you're free to still use that, but make sure you know how to do this without help, because on the AP test, remember, you won't have that foldable. You won't be able to, you have to know how to do this process. Okay, so a way to know how to do this process is we're looking at the units, right? So our units, if we're going from inches to feet here, right? For our units to cancel out, they have to be on opposite sides. So whatever unit we start out with, that needs to be on the opposite diagonal. So inches go on top and inches on bottom cancel out. We're left with the feet or foot. That becomes our unit for our answer. Okay. And remember, with dimensional analysis, our molar masses is dependent on the compound. So if you're ever going between grams and moles, you need the molar mass. That's from the periodic table. If you have a diatomic molecule, so remember, those are any that have two of the same element. So H2, N2, O2, F2, Cl2, Br2, and I2, those are diatomics. If you have two, you add up the mass 2 times. So O2, oxygen has a mass of 16, but if we have two of those, O2 is going to actually have a mass of 32, not 16. Be careful with that. That's an easy way to get tripped up. Okay. So remember, molar mass has the units of grams per mole. Okay, so either the grams, 32 grams on top per 1 mole of O2, or you could do 1 mole of O2 on top per the 32 grams on the bottom. For molecules, anytime we're talking about molecules, atoms, particles, electrons, any of that, you can use Avogadro's numbers to go between moles and those. So 1 mole is 6.022 times 10 to the 23rd. And when we're talking about gas laws at STP, you can go from 1 mole to 22.4 liters. So you can convert from moles to volume. Okay. And a good habit to build is whenever you're doing dimensional analysis, so for these right here, I didn't do it up here, but what you should do is you should have the number, the unit, so 32 grams, and what you're talking about, right? 32 grams of what? We're talking about O2 here, O2. Okay, so 32 grams of oxygen gas per 1 mole of oxygen gas. That makes it easier to talk about the units and the elements, and it makes it easier to cancel things out because you're going to have grams of different compounds and you don't want to get confused about what you're talking about. Okay, so a good habit to build is write the number with the unit and with the compound you're talking about. All right, so stoichiometry, this is the dimensional analysis, but we're not, so dimensional analysis was just looking at one side of this. You're not changing the compound. Stoichiometry, you're going between two different compounds, right? So you're going between the X's and the Y's. You're going between two compounds, okay? Stoichiometry is very important in chemistry. It is a foundation for chemistry. You need to know how to do this. And this tells us how much we're going to use when we do an experiment, how much we're going to be making of each product, and it tells us what our limiting and excess reactant is, okay? So make sure you know how to do dimensional analysis, know how to do stoichiometry. These are very important. You'll use this in every unit we do. Okay, so let's do some examples with this. All right, so if we have, let me leave the map in there so we can reference it for this part. For the first one, we have this equation up here. We have the reaction. The first question asks, how many moles of lithium hydroxide are needed to react with 20 moles of carbon dioxide? Okay, so in here you also see why name is important. What is lithium hydroxide? That's going to be our LiOH. Carbon dioxide is our CO2. You need to make sure you know what those are. So we have what we're looking for, moles of lithium hydroxide, and we have what we're given. We have 20 moles of carbon dioxide. So we're going to start with your given, your 20 moles of CO2. You can put this over 1. You don't have to do the over 1 part if you don't want to, but it helps some people. And to get to moles of lithium hydroxide, right, if we are starting here, moles of X, we're trying to get to here, moles of Y. So we're going to use a mole ratio. Remember the mole ratio, we are looking at the coefficient to our equation. So that's when you need to do balancing. If you don't remember how to do balancing reactions, make sure you look over that, ask questions. but sometimes you typically won't be asked directly to bounce an equation. It'll be normally be given to you like this. Okay, so we're looking at those mole ratios. If we're starting with moles of CO2, then our moles of CO2 should go on the bottom so that can cancel out, and moles of LiOH goes on top, so that could be our final unit. That's what we're looking for. Okay, so CO2, there's no number in front, so we only have one. Lithium hydroxide is over here. We have a 2 in front. Okay, so we're going to multiply the number by 2. We get 40 moles of lithium hydroxide. Okay. From this, so if we again have 20 moles of carbon dioxide, we're looking for how many grams of water. Okay, so again, let's start with the 20 moles CO2. In our diagram now, we are starting with the moles of X, same place, but this time we're going to do something a little different. We're going to go to mass of Y, mass of water, the grams of water. So we can't go there directly. We have to go to moles first, then from moles to mass. Okay. So to get this to moles first, right, we're going to do that mole ratio, same thing we did above. So we're going to have our CO2, moles of CO2 on the bottom. We said that was 1. And we need moles of H2O on top. Again, there's no number in front, so we only have 1. Then for grams, right, if we had moles of H2O there, we need moles of H2O on the bottom. And we're going to grams of H2O. That'll make our final units grams of H2O. All right, so to find the grams per 1 mole of H2O, this is our molar mass. This comes from the periodic table. So on the periodic table, hydrogen is going to have a mass of 1. It's 1.008, but you can say 1. Oxygen has a mass of 16. It's 15.999. You can say 16. We have 2 hydrogens, 1 oxygen, H2O. So the total mass is going to be 18. So it's 18 grams of H2O. Okay. If you do the math there, 20 times 1 times 18 divided by the ones, right, you should get 360 grams of H2O. Right? And the last question, if a chemical reaction occurs that generates 57 moles of lithium carbonate, that's our Li2CO3, how many moles of each reactant was used? Okay, so let's look at our map first, right? We are starting with our moles of lithium, 57 moles of lithium carbonate, moles of Y, or moles of X, whichever one you want. And we're going to moles of reactants. So we're doing a mole-to-mole ratio, but we're doing this twice because we have 2 reactants. So we're going to set this up the same for either one. We have 57 moles lithium carbonate okay. For the first one, we're going to our first reactant, let's say CO2. So we're going from moles of lithium carbonate to moles of CO2, right? And that is a 1-to-1 ratio. So that gives us 57 moles of CO2. For our second one, we're going to LiOH, lithium hydroxide. So on the bottom, we need the moles of lithium carbonate, which we said is 1. And lithium hydroxide has a 2 in front. So 2 moles lithium hydroxide on top. So 57 times 2 is 114 moles of LiOH. Okay, so if we look at our answers here, we get 57 moles of carbon dioxide and 114 moles of lithium hydroxide. When we talk about limiting and excess reactants, right, these are 2 reactants. We have less carbon dioxide here. That means it'll get used up first. If it gets used up first, that's our limiting reactant. The one that we'll have left over of is our excess, right? Because even in English, excess means you have left over. So our excess is left over. Our limiting is what's all used up. When we're trying to find how much product we'll make, we're only going to use our limiting number. We're not going to go based off the excess. Because if we use our excess, we're going to be making more of our products than what we actually make, because we're going to have leftover from here. All right. So we'll do a lab on limiting and excess reactants. We'll talk about that a little bit more. But that is the end of these notes for Unit 0. So that is everything that we're going to talk about from, or it's not everything, it's most of what we're going to talk about from what you've already learned in chemistry. Some of it we'll bring up as we go along. So for example, advanced, you guys talked about acids and bases. Everyone talked about thermodynamics. We'll bring those up again second semester when we actually talk about those units. All right, but that is the end of Unit 0. Make sure you work through, finish the notes, write down any questions you have so you can ask me them or ask each other. And then make sure you start working on that practice packet. You'll have some class time to work on that, but anything you don't finish in class, you will need to do before the due date, which is the day of the test. All right, so let me know if you have any questions, but have a great day.